Hi, my name is Scott Neal. I'm the Company Safety Coordinator for Detroit City Power, and today we're going to go over how we use quantitative methods to ensure the health and safety of our workers at the Jenkins Welding Center. Our company, Detroit City Power, takes the health of our workers quite seriously. At our Jenkins Welding Center, based on the west side of Delta City, welders perform repairs on damaged electrical equipment or assemble newer equipment. This type of welding work releases hazardous metal fumes. At Jenkins Welding Center, quantitative methods are used to measure the exposure of our workers to metal fumes. Using quantitative methods, we are able to measure how much power is needed by the fans in our ventilation system to clear workstations of fumes and gases. Of primary concern are hexavalent chromium fumes. We use the following equation: Q equals 403 times specific gravity times evaporation rate times K, which is a safety factor, times 1 EB, which is a conversion factor, divided by molecular weight multiplied by threshold limit value. Q equals a flow rate, as you can see from the listing of variables, and we use Q to determine how much airflow the fans will need to remove harmful fumes. The threshold limit value of hexavalent chromium at a workstation more than 12 inches above the station's table is 0.00235 parts per million. The molecular weight of hexavalent chromium is 52 grams per mole. The specific gravity of hexavalent chromium is 7.19. Its evaporation rate is 2.7 pints per 60 seconds under welding conditions, and we have set K at 2. After performing the necessary calculations, we've discovered that the necessary Q needed to establish a safe working environment is 2,134 cubic feet per minute of airflow through the fan. This diagram shows how the fan works. A vacuum is placed near an active weld and sucks in fumes, using a fan to generate higher pressure on the opposite side of the ventilation system, which causes the fumes to move into the vacuum and be deposited in a fume depositing tank. Here are two of our workers, both welders, one holding the vacuum fan and the other working on a small weld, and this demonstrates how this system is used in real life. This is a ceiling fan at the Jenkins Welding Center. I put this in the slide to generate that we use the same principle for our other fans, and we also do calculate Q values for ceiling fans as well. To conclude, a flow rate of 2,134 cubic feet per minute will be needed to ensure the safety of our welders. The current flow rate is 1,500 cubic feet per minute. This meets the safety requirements, but at a lower K value. For the safety of our welders, the flow rate should be upgraded to between 2,100 and 2,200 cubic feet per minute. Before making these changes, the time-weighted average, or TWA, of hexavalent chromium and the individual hourly measurements were the following. The measurements, which we refer to as X, are listed here. As can be seen, measurements 2 and measurement 6 are over the permissible exposure limit for hexavalent chromium. The time-weighted average equation has yielded a 8-hour time-weighted average of 0.0021075 parts per million, which is below the permissible exposure limit. As can be seen, the TWA is acceptable, but there were two individual measurements that were over the permissible exposure limit. After performing the equation to find Q, the flow rate, and increasing the flow rate to between 2,100 and 2,200 cubic feet per minute, the TWA was the following. The measurements, which we will again refer to as X, are the following, and as can be seen, there are no individual measurements that are over the permissible exposure limit. The time-weighted average for these new measurements was equated as 0.00139 parts per million. The new time-weighted average is lower than the old time-weighted average, and there were no violations of the permissible exposure limit in the individual measurements. This is of great benefit to the safety and health of the employees at Jenkins Welding Center.